On occasion, it will happen with these substitution rule problems that it'll be necessary to make multiple substitutions within one single problem. Allow me to demonstrate. We have the indefinite integral of x times the square root of x plus 1 times dx. Now, upon initial inspection, I see that the square root of x plus 1 would count as a composition of two functions. So my initial thought is we could say let u be equal to x plus 1. Now, in the event that we'd like to do that, our differential substitution is going to be du is equal to whatever the derivative of this is. That would be dx. Now, the thing that I'd like to point out is that that means we now have a substitution for the x plus 1. We now have a substitution for the dx. But what we don't have a substitution for is this initial x. However, because I have this statement up here, I can solve this for x to create an additional substitution. So this x will become u minus 1. After I make these substitutions, u minus 1 times the square root of u times du, a little bit of algebra will help us get this to a form where we can integrate a little more effectively. So treating the square root of u as u to the 1/2 power, we distribute through the parentheses to give us u to the 3/2 power minus u to the 1/2 power du. At this point, we can employ the power rule for each of these. So 3/2, we add 1 to that power, we get 5/2, and divide by the new power, multiply by the reciprocal. Minus, do the same thing for this, u to the 1/2 power goes up by 1, and we divide by the new power, or multiply by the reciprocal. Now that the integral is done, we can add on our plus c. And substituting back each of these u's is going to become an x plus 1. For a final answer of 2/5 times x plus 1 to the 5/2 power minus 2/3 times x plus 1 to the 3/2 power plus c. I would like to let you know that there is another take that you can make on this problem. What we're going to do is create what is known as a rationalizing substitution. It happens very frequently with these radical problems that making a substitution on the radical itself is a possibility. So if we let u be equal to the square root of x plus 1, rather than trying to make the differentiating substitution in its current form, I'm going to do as we did before and actually solve this for x. Upon doing so, I would get u squared is equal to x plus 1, or simply x is equal to u squared minus 1. If I were to differentiate this to create a differentiating substitution, I would get that dx is equal to 2u times du. When you do this, it guarantees that you'll have a substitution for the dx to go directly in terms of u. This doesn't always necessarily happen this nicely, but it certainly can happen from time to time, especially when dealing with radicals. So with that in mind, if I make these substitutions, the x will become u squared minus 1. The square root of x plus 1 will simply become u, and the dx will be substituted as 2u times du. A little bit of algebra, specifically the distributive property, says we can take the 2u and the u and distribute to both of these terms to get 2u to the 4th minus 2u squared du. Integrating each of these will simply be a use of the power rule, where we increase each power by 1 and divide by the result. Now with that in mind, the initial u being the square root of x plus 1 means that we could also express it as x plus 1 raised to the 1/2 power. If you take a 1/2 power and you raise it to another power, you multiply the exponents. So this would be 2/5 times x plus 1 raised to the 5/2 power. minus 2/3 times x plus 1 raised to the 3/2 power. You'll notice that that result is consistent with the result that we got from the other substitution. So on occasion, there are multiple ways that you can do any one single problem.